lots of different sounds to choose from. Right? And if I want to build a controller where I use this leap motion to control this, I've got to program a mapping function where I've got 15 inputs controlling 9 outputs, and everything's continuous. So that's pretty complicated. It's going to take me a long time if I just sit down and try to program it. So what I'm going to do instead is use, let's see, I've got 15 inputs and 9 outputs. I'm going to use a straight up multi-layer perceptron neural net for each one of these outputs, and I'm going to start by finding a sound I like and saying, all right, I want that sound to happen when my hand is here. So here's one sound, and maybe I want the pitch to go up when my hand goes up. And so here's another sound, and let's see if it learned that. Right, now I've got a stupid theremin kind of thing, and I can start making new sounds, and maybe I want, that's my favorite one, I want that to happen when I start doing this claw kind of thing, right? And now I can... Let's turn that up a little bit. All right, so that's a lightning fast demo. Right, clearly faster than making a 15 to 9-dimensional mapping function by writing code, even if you're a really quick programmer. So what is, why do we care? As you saw here, using this training data.
You want me to keep going?
All right, no, that's good. Does anybody have any questions about the demo that you just saw? All right, I'm going to take that as a no. So I guess the next part of my talk, I just want to talk about some of the reflections that have come out of this work. As I said, I've been using the first version of Wekinator and then subsequent versions of it with composers since about 2008. I've also used it with a bunch of other people. I use it a lot in teaching. I use it in teaching university, but as well also teaching high school kids, for instance. I've done some work recently using it to build customized musical instruments for people with disabilities. I've used it to classify cello bowing articulation gestures, beatbox vocalizations, these sorts of existing musical gestures where you're not trying to make a new instrument, but you're trying to understand what it is that someone's doing. I've used it in some rehabilitation and motor learning research. And most recently have a big project here at Goldsmiths around building better prototyping and development tools for startups. So here the users are not composers, but they're people working at a startup trying to build tools that can be easily customized with machine learning. So I've got papers on all of these things. If you're interested and want to hear more about something, ask me a question or send me an email. But from all of this work, I've spent a lot of my time trying to understand, what is machine learning really good for in these contexts? What are the musical consequences of using it? How can we do even better than off-the-shelf machine learning tools in making machine learning or similar interactions that help instrument builders or students or people with disabilities, and so on. So I'm going to go through a few findings here. Again, feel free to interrupt and ask for follow-up questions. The first thing that I learned, this was quite surprising to me as someone who had mainly done music information retrieval research and wasn't thinking so much about the importance of the design process, is that these algorithms, I was using things like Nearest Neighbor, AdaBoost, neural networks. These algorithms weren't made to design creative interactions. They were made to make accurate models from a training set. But in practice, when I talked to composers who were using Wekinator and said, all right, why are you using this? You could do things lots of other ways. It wasn't that they said, oh, I can make more accurate classifiers. I mean, certainly machine learning does allow you to make more accurate classifiers than writing programming code if you have a good data set, but that wasn't the primary hook for them. It was the fact that using the tool the way you saw me use it in the demo supports the kinds of things that composers really value. When you're making a new instrument, you start out with a basic idea of what you might want to do. You say, all right, I've got these sensors. I might want to move in this way. I've got some sounds that I think are really cool. I want these to be connected together somehow. And you might have an initial idea of how to do that. If you write code to make that mapping, it may be several hours before you actually have something that you can try out. And then you might spend several days or even weeks refining that until you get to the idea that you had in your head. And by that point, you might be out of time, and that might be it, and there's your instrument. However, with machine learning, if you can build that sort of initial prototype idea in 30 seconds, that gets you to a point where you can test it out and say, is this really a good idea? You know, do I really like it when I move my hand like this and I hear those sounds? Are those sounds that I really like, or do I need something that's slightly different in timbre? And so what you see in practice is that people end up often spending the same amount of time building instruments as they did previously writing code, but they're able to explore lots of different alternatives in the same amount of time. And they're able to try something out and say, okay, this is what I like about it, this is what I don't like, and based on that assessment, I'm going to refine the aspects of it that I don't like. And so those are things that are really, they're hard to do in programming, and they're especially hard to do efficiently in programming, even if you're a really good programmer. So that's, the first point that I want to make is that the utility of machine learning here is quite different from the utility of machine learning in more conventional applications. It's really about speeding up the design process, allowing people to make lots of things rather than to just make one thing that they may or may not be happy with. So a second important difference between this and a lot of other machine learning applications is that, as the person tries out these different designs, that person is adapting to what they've learned about the design space. And in most machine learning applications, there's this idea of a ground truth, that you have this concept that exists sort of underlying your training data, and your goal is to model that concept as accurately as possible. But here, if you think about building a new musical instrument, there are lots of instruments that you could potentially build, right? Even just thinking about a simple case of classification, you might say, all right, I want to make a style classifier that listens to me and classifies the style that I'm playing. Well, how many style classes are there, right? Or I want to make a beatbox classifier. How many classes is that, right? Is it 3? Is it 20? There's different ways of formulating the learning problem, and some of those formulations are going to be really easy to learn for the computer, but they may not be that useful to you. On the other end of the spectrum, there may be really fine-grained problems that are going to be harder to learn. They're going to require a lot of training data. They might require you to spend a lot of time figuring out what features you want to use, but in the end, if you build something, it's going to be more useful. So what you see in practice is people navigating this space and constantly, as they give training examples and test out the model, they're not just trying to improve the model, they're actually changing their own opinions about what is feasible in this space, what do I really, how do I want to spend my time getting there? And again, that's something that I think is applicable not just in musical instrument building, but in a lot of applied machine learning applications, and this idea that the human task of defining the machine learning problem, that's not usually something that's explicitly supported by tools. And I think there's a lot of room here for good research to build better tools. And again, you can find some of this research in the CHI conference, for instance, over the last few years. One paper that I did with a couple students explored this, and we said, all right, put aside Y Combinator. We're going to build a totally new interface just to allow people to explore how many classes they might want to use for a learning problem, different alternative formulations of different classes. If this is interesting to you, you can go read that paper. All right, the third thing I want to mention is that when you're talking about something like building a new musical instrument, composers, musicians, they have a lot of embodied expertise that they bring to the table, right? They have the ability to move in certain ways. They have great ears that are very highly developed. And programming doesn't really allow them to take advantage of that expertise in a direct way. Whereas if you say, all right, show me how you want to move, or show me what you think the performer is going to want to be doing with this assemblage of sensors, that's really easy to do. So here, again, machine learning offers us one way into allowing people to more directly communicate their intentions about what they want an instrument to do. I've got another set of work that I've just started publishing on in the last few months, where instead of saying, all right, we have to use supervised learning to allow people to communicate this to a computer, we might use other approaches. I've got some slides. Let me see if I can find this slide easily. We've been doing some work around something called grab and play mapping with people who have disabilities. So one thing that has ended up being really useful is to say, all right, instead of showing, here's me doing one thing and here's the sound that should happen, and here's me doing another thing and here's the sound that should happen, let's just give the sensors to someone and say, show me how you want to move. Show me how you want to move in a way that's comfortable. And then we have a sort of hacky algorithm that builds you something, right? Obviously, it's not going to build you something that encodes your understanding of how gesture and sound relate to each other, but it's going to give you something that you can play with. And if you don't like what it's built, you can just hit a button and build a new one, and it'll build you a new thing. Or if you want to refine it, you can start from this and go back to a supervised learning paradigm where you say, all right, now in this part of the input space, when I move like this, I do want you to play a sound like that instead of what you're doing right now. So you can kind of mix this up with supervised learning. I actually have a question. Is Chris Laguna in the room?
No, he's not here.
No, he's not here.
Oh, darn. All right.
You got called out.
This is actually something that the roots of this project are in some of the work that Chris did when he was doing an internship with me a few years ago. So he's missing it. All right. Let's see. Go back to my slides. All right. The next thing I want to mention is that, especially in this kind of creative space, people may have an idea that they bring to the table about what they want the computer to do, but they're often open to changing their mind, right? They're often open to saying, oh, it made that one sound when I did this thing, and that's a really cool sound that I didn't know the synthesis algorithm could make, and I want to hang on to it. And again, that's something that you can reinforce using supervised learning. You can put more training examples back into the training set and retrain to reinforce that behavior. And that's quite interesting. Again, totally different from a lot of more conventional machine learning applications where you really don't want to be surprised at all by what the computer does. And again, that's another motivation behind the grab and play project that I just mentioned to you, in that lots of times people even don't have any idea what kind of sound they want to make. They just want to say, all right, I want to use these sensors, and I maybe want to use this synthesis algorithm, and I have no idea what the design space is. And so getting supervised learning out of the picture and using something else that will generate you a mapping function given some examples of inputs, unordered, unlabeled, and maybe additionally some constraints on the output space. I think that's a really interesting kind of way of formulating this problem, and there's lots of ways you can implement that. So that's work that I'm just starting to do with one of my students. All right. And again, asking composers why they've used this when they could be using something else. Without machine learning, you get words like, well, it's inspiring. It's something that makes me think differently about the process. And Letitia Tsunami especially has some really interesting lectures about machine learning that you can watch online. She talks about this nature of interaction between her and the instrument, as it's being very important to her that it's not just a simple matter of control, right? She says, you don't want the instrument to perform like a well-trained animal circus. You kind of want it to be a little wild. You want to adapt to it somehow, like riding a bull, right? If you go into the literature in the NIME community, you'll find people writing about this relationship between people and instruments, right? And one of the great promises I think that digital technology gives us is that we can build instruments that may not be just things that we spend a decade learning how to control, right? They can have they can have agents, they can do things that might be non-deterministic, and Chadaby especially writes about how you may want to not just build something that mimics an acoustic instrument and that it does the same thing every time you do a certain motion. A lot of the composers I've worked with, they don't want to build that kind of instrument, right? The Wekinator, the version that you saw in the demo, is going to give you a deterministic model. So if you give it the same input, you're always going to hear the same sound. But what we've, or at least the way that I think of it, is that we've taken that sort of non-determinacy, that sort of aesthetic challenge, and we put it into the composition process or the instrument building process. So that's one of the reasons that when I write about Wekinator, sometimes I call it a meta instrument, is that this process of creating an instrument itself is or can be very creative. It can be creatively engaging and expressive. All right, let's see. Another couple of things that I want to point out here. I think a lot of students, especially who I work with, who start using machine learning in their work, they always want to build a gesture recognizer. They say, I want to build something that when I wave my hand, it does one thing. When I do this other thing, it does some other thing. That's okay, but you can do that with a button. It's not that musically interesting. It may give you more for the audience to look at than someone sitting behind a laptop typing. But most of the professional composers I've worked with have really wanted to build something that is more complicated. And again, if you go look at say, Andy Hunt's writing, Marcelo Wanderley's writing about musical instrument design, they've got some really interesting research suggesting that having continuous multidimensional controllers where you have complicated relationships between the ways that you're moving and the ways the sound is changing, that can actually be more expressive, can invite people to explore the instrument with a different mindset even than something that is a little bit more prescriptive. And one of the interesting findings that's come out of my work with people with disabilities is that a lot of the community events that I've run, we have people from the community coming in, picking up an instrument, playing with it. And these aren't professional musicians. They're not trained machine learning experts. They've maybe never even played with computer music systems before. They've also found that these continuous multidimensional controllers are often the most satisfying. If you think about something like the Leap Motion demo that you saw, there's no wrong way to play it, right? Everything you do makes a sound. You can come up with your own sort of gestures within the space, and they are going to correspond to musical gestures. And each person might be able to play that in a totally different way, and you get your own bespoke sound kind of for free from that. And that's been surprisingly powerful for the kinds of community groups that we've worked with. All right, that's the paper I just mentioned. It's from our Kai publication last year. All right, a couple more things I want to mention. So this is for those of you who've done some machine learning stuff. Before, I want to come back to these questions about how you train effectively on this data. One of the interesting findings that we've seen over and over again is that the training examples that people provide are quite different from the training sets that you might use in an application for, say, the music information retrieval space. And one of the first things that becomes very apparent is that the data that people provide is often very much not IID, right? You can't think of it as, all right, I saw lots of examples of this type and a few of that type, and therefore when I run this instrument in the future in performance, the performer is going to be doing a lot of this thing and not a lot of this thing. That's totally not what happens. What happens more often is that people teach the computer in ways that are similar to how people teach people. And if you think about, me trying to visually demonstrate to you different hand gestures, I might say, all right, here's hand gesture 1, and here's hand gesture 2. right? And what I just showed you there are two canonical examples, right? You think about these as like right in the middle of those classes in the feature space. And then, if you've learned that, I might start showing you different hand gestures and seeing what you do. And eventually I might find that, okay, when I do something like that, you might get that wrong, right? And then I'm going to say, okay, no, I'm going to give you a corrective example and say, no, this is still an open hand, even though my thumb is pointing up. And that's basically what people do with Wekinator, right? They'll start out by giving canonical examples. They'll test it out and say, all right, well, here's the decision boundary that ends up being drawn in that space. And I don't quite like that, so I'm going to give it some more examples of things that are near what it got wrong, right? And then I'll retrain it, and I'll get a better decision boundary, and I'll keep doing this process. So what we have is examples that are sort of canonical. We have examples that are really, they're almost like support vectors in an SVM. They're kind of nudging the decision boundary somewhere else. And if you take that information, you think about the standard machine learning algorithms that you might use, that isn't a model of the data that's explicitly taken advantage of by any of those algorithms. And one thing in particular that you notice is that algorithms that you would say are the really good algorithms, certainly the latest craze in machine learning is deep learning. That's not applicable here because you don't have enough examples most of the time. Before that, it was SVM and AdaBoost. Those are not going to work so well here because they're often going to they're going to prioritize making smoother boundaries over listening to all these points, right? Whereas something like nearest neighbor, you can give it weird points in totally arbitrary parts of the space, and it's going to do what you tell it to do. So for that reason, nearest neighbor is the default classifier. Built in Wekinator, you can change it to something else, which is probably good if you've got really noisy data, and you don't have careful control over where you put these points, but often nearest neighbor works surprisingly well. So that's an important finding. Another thing that we saw quite surprisingly in some of our work is that if you think about conventional machine learning contexts, people might evaluate classifiers using something like cross-validation. Because of this property of the data, it's not IID, you actually may find that cross-validation doesn't give you reasonable information at all. So with that, I realized we're running kind of short on time. I wanted to see if people had questions that they wanted to ask based on what I've said.
Any questions? Yeah, we have one in the back.
I got a really...
Well, why don't you come up here?
You have to go, yeah.
So you can hear you.
I've just got a really low-level question. So, like, when you were doing the audio control with Max, and you changed the parameter, and then you learned it with the Wekinator, does that mean there's two-way control going? Because you would change a parameter, and then...
Yeah.
Okay.
Yeah, so there's some open sound control messages happening behind the scenes. If you wanted to build a sort of totally new skin for Wekinator, you can almost completely do that with OSC messages.
Okay.
So I've done that in some projects.
All right, thanks.
Yeah. Any other questions?
Don't be shy. Yeah, we have one over here.
Last year we were using Wekinator in our interactive music class. A lot of us have made interfaces and like gloves and the Wekinator was one of the tools that Professor Jason told us about, and along with MLlib. So what I wanted to know from you is, in your experience, what does Wekinator lack in? So it's really quick, but I felt that when we were trying to train a lot of gestures, it would not really be that robust. So according to you, what are the points where it lacks right now?
Yeah. So I guess my first question is, were you using the new version of Wekinator with the white interface, or were you using the old version with Chuck built in?
No, we were using the old. I was using the old. I don't know about the others.
Okay, so the old version was lacking lots more stuff than the new version. The new version is, I think, a lot better overall, but there's still some I think, key challenges. So number one, the version that you download right now, it is only supervised learning, right? It's classification, regression, and dynamic time warping. It doesn't directly allow you to do, these actions that I'm talking about, where you may not know exactly what you want to build, and you want something to more efficiently allow you to explore the space. So that's the Grab and Play project is starting to address that. The thing that you mentioned of, if you start trying to make a classifier, as the number of classes you have grows, things become really hard. One of the main reasons that happens is that Wekinator doesn't do anything intelligent with features, right? It doesn't do feature engineering for you. And if you're using audio or you're using sensors or video, the way that you extract data from those devices has a huge impact on what you want to learn. And that becomes, right now, I think that's the bottleneck of, that's the hard stuff. And you have to do a lot of programming, you have to do a lot of manual experimentation or brute force searching over different engines. And so that's something that I think will definitely be improved. Deep learning is helping a lot for coming out with better feature representations for audio and video. But again, that's predicated on having a really big data set. So some of the ways that you can address that are using transfer learning, for instance, where you use deep learning to get your basic features, and then you apply this sort of interactive machine learning on small data sets on top of it to tune the deep learning to learn a concept that's more relevant to you. But yeah, the trade-off of that is that can still be really slow. So I think that those are two really big issues.
Yeah, that makes sense. Thanks.
Oh, cool. I think
That's a good question.
I think we're out of time because some of us have class in about 10 minutes across the campus. We'll
All right.
next door. Thank you so much for joining us today. And I'm sure if they have any more questions, they will email you.
Yeah, do get in touch. Thanks so much for having me. I want to mention before you guys take off that if you are using Wekinator again this year, there's a new website with a help forum, and I'm also teaching a MOOC. So if you go to Cadenze, you can sign up for the MOOC and watch all the videos you want for free. So that's probably the best resource for learning about Wekinator, but also learning about machine learning in these kinds of interactive contexts.
That's cool. I think it's
All right. Thank you. Bye.
All right, thank you. We have only, I think, 2 more seminars.